Hello everyone, my name is Daniel and I'm a Microsoft MVP on developer technologies. Today I'm going to talk about Semantic Kernel and I will show you how to use Semantic Kernel to build OpenAI plugins. I will also demonstrate how the plugin works and I will share with you some of the challenges and benefits of using Semantic Kernel. I presume that most of you are familiar with ChatGPT or Bing Chat. How are you building your prompts? Do you have a stash of magic recipes? I think we all have some. Using Semantic Kernel, we can benefit of the power of large language models for natural language understanding and natural language generation, reducing the complexity to work with them directly. So, using Semantic Kernel, we don't have to learn the particularities of all these models and APIs. Instead, we can use the Semantic Kernel intuitive interfaces. With Semantic Kernel, we can orchestrate AI plugins that interact with various services. Even more, we can combine large language models like GPT with traditional programming languages to enhance our applications with natural language features. But what is Semantic Kernel? Semantic Kernel is a new open source SDK from Microsoft that allows you to easily integrate large language models services like OpenAPI, Azure OpenAPI, Hugging Face with traditional programming languages like C#, Python, and Java. What truly sets this Semantic Kernel apart is the ability to orchestrate out-of-the-box plugins or user-defined plugins using AI, in fact, GPT. Let me explain. These plugins include prompts and native functions that can interact with the real world. They are like the body of our AI applications. On the other hand, Semantic Kernel introduces connectors that bridge the memory and the models. They are like the brain of our AI applications. These components can then be orchestrated using Semantic Kernel pipelines to fulfill user requests or to automate complex tasks. First, let's talk about differences between GPT and ChatGPT. Well, first let me make it clear. As humans, we are using ChatGPT web interface in a conversational manner. But as machines, we are going to use an API, which is more flexible and more customizable. GPT is a language model, not an application, not even a service. GPT can be tailored to build different functions like text summarizing, parsing text, translating languages, and many more. And GPT has an API that lets anyone use the GPT-3 or GPT-4 models to build their own AI applications. So, OpenAI API is such a web-based interface that allows users to access various AI models, such as GPT 3.5, GPT-4, DALL-E, and more. OpenAI API is mainly used by developers who want to build applications. Does OpenAI API search the web for knowledge? No. OpenAI API does not search the web. The models generate responses based on patterns and information in the data they were trained on. In fact, models does not keep knowledge at all. Another question. Does OpenAI API deal with the state? No. OpenAI API is stateless. This means it doesn't maintain or remember information between different requests. This is good for security, right? Each request to the model is processed independently of others. so the model does not have the ability to store information or context from one request to use it to another. Then, what are ChatGPT and Bing Chat? Well, ChatGPT and Bing Chat are both powered by large language models, and they are designed for the general public who want to interact with an AI assistant to engage people in conversations with the AI, asking questions, getting help with tasks, and more. I have another question. Are ChatGPT and Bing Chat stateless? Well, still, they are stateless in the sense they do not maintain or remember information between different requests. Each conversation is independent and does not have access to past conversation. But what is a conversation? When having conversation with ChatGPT, we notice it maintains a history of around 20 prompts. Bing Chat maintains like 30 prompts. Therefore, maintaining the context of a conversation becomes the responsibility of the application, like it's ChatGPT or Bing Chat, the application using these APIs. But OpenAI API does not maintain a state. So what is the place of semantic kernel in all this story? Well, semantic kernel simplifies interaction with large language models. Semantic kernel orchestrates complex prompts organized in plugins. Semantic kernel combines large language models with traditional programming to build plugins, and it deals with the context. Semantic kernel is a powerful tool that will make it more efficient to build sophisticated AI applications. We have the chance to see how in the next slides. Let's address a fundamental truth. Garbage in, garbage out. The semantic kernel is engineered by ensuring that the input you provide produces meaningful and valuable output. So we understand that critical information of data quality, and the semantic kernel is going to help with this. How similar are the prompts we are using already for ChatGPT with the prompts we are going to use for our applications? Are they similar? Let's see. When using the ChatGPT web interface, you are primarily focused on crafting prompts that will lead to meaningful and engaging conversations. This could be considered prompt building. On the other hand, when using the OpenAI API, you are not just crafting prompts, but also you are managing how the model interacts with these prompts. This includes handling things like token limits, response length, temperature settings, and more. So we call this prompt engineering. Using prompt templates to parameterize the prompts allows dynamic data to be passed into the prompts, enabling more flexible and context-specific interaction with the model. So this is prompt engineering, not prompt building. But let's see what are prompt templates. Prompt templates and prompt template syntax are used to define and compose AI functions using plain text. They allow you to create natural language prompts, to generate responses, to extract information, to invoke other prompts, or to perform any other task that can be expressed with text. Here are the basic features of the prompt template language. variables. In this template, $name is a placeholder that would be replaced with the user's name when the template is used. Function calls. In these templates, weather.getForecast is a function that is called with $input argument by default. So, $input argument is optional, but it's there. Function parameters. In these templates, $city is a placeholder where the city name, a variable in fact, and weather.getForecast $city is a function with an argument. Of course, we can use a hard-coded value for the city to skip the argument if we prefer. But what are semantic functions? For building semantic functions, we will consider a concept called text in, text out. The text in, text out concept refers to the primary interface through which you can interact with the language model. You provide an input prompt containing text, the text in, and the model generates a text completion, the text out. As we can see in the code sample, semantic functions are essentially prompts that are sent to an AI service, along with additional settings that AI service requires. By default, semantic kernel recognizes input variable by default, but if we want to create additional variables, we need help by using context variables to set them. The rest in the code sample is like in the previous slide, passing the prompt and the prompt itself and additional settings to the AI service. We are not limited to running the functions one by one. Instead, we can chain them together. Similarly, we have the context variables with an interesting twist. The output of one function in the chain will be the input in the next function in the chain. But what are native functions? Native functions are used to perform tasks that large language models cannot perform on their own. These tasks include retrieving data from external data sources, or knowing what time it is, then performing complex math operations, or completing tasks in the real world, or memorizing and recalling information, and more. Did you notice the SK function attribute in front of the class methods in our sample? By annotating the method with this attribute, we instruct semantic kernel that this method is a native function. In addition, you can notice the description attribute in front of the method arguments or in front of the function. We have to choose carefully these descriptions because the plugin quality depends on these descriptions. When writing description, follow the next guidelines. The description field should be short and concise so that it does not consume too many tokens when used in a planner prompt. These variables are passed from one function to another. Then, choose sufficiently unique description for the other functions in the same plugin. If they are not, Planner may not be able to distinguish between them. We don't want that. And if we have trouble getting Planner to use a function, try adding recommendations or examples how to use the function in the description. What is a plugin? Well, a plugin contains semantic functions, this is prompts, and native functions, this is traditional code. A plugin contains a text file named skprompt. This includes a prompt template. The prompt template is created using prompt template syntax with variables and functions. Semantic kernel will render your prompt template replacing the variables and the functions placeholders, and it will execute the logic behind it. A plugin contains a configuration file called config.json that includes the prompt template settings. This is similar to prompt template settings class that we discussed before. And a plugin can be used directly in our application, but it can be exported and use it with ChatGPT or Bing Chat or Microsoft 365 as well. Both semantic functions and native functions are implementing ISK function interface. Therefore, they can mix together in the same plugin. In Semantic kernel, there are core plugins like text plugin, time plugin, math plugin, file IO plugin, HTTP plugin, and more. But we are not limited to them. Most of the times we are going to create our own plugins. Let's conclude. We have two ways to create the plugins. The programmatic way, using the prompt template config along with the prompt template, or by providing skprompt text file and config.json file in the plugin folder. Please notice that the fixed folder structures have to be followed. Now, let's build a motor plugin that I'm using in the demo that follows. The purpose of this is to build a semantic interface over a car robot API, the traditional API, which is capable of basic movements like going forward, going backward, turning left, turning right, and stop. I have a pet project with such API, and the next challenge was to teach it to move in more complex patterns, not only turn left, turn right, forward, backward. So, first we define all the native functions we are going to use. No more, no less. And by choosing a good description, we hope the planner will have some good functions to choose from. Then we instantiate the kernel, we define the prompt, then import the native functions from the motor plugin, and then import the orchestrator plugin. This is a special plugin which is finding the best match for our intention in the imported plugins functions. And finally, we run the best match, the function where the orchestrator routed us. In the previous slides, we have manipulated the functions from the register plugins in a programmatic way. But there is a more intelligent way to deal with functions by using AI or GPT, and we can achieve that by using planners. A planner will choose a function or a list of functions, depending on the planner, from the register plugins to accomplish a goal. So, what is a planner? As I said, we have manually orchestrated all the functions on behalf of the user, but this is not a scalable solution because it would require the application developer to predict all possible requests that could be made by the user. Instead, we will learn how to automatically orchestrate the sequence of functions on the fly by using planners, of course. A planner works by mix and match the functions from the registered plugins into a series of steps that completes the goal. However, I will say it again, it's crucial to ensure that only functions intended for use are exposed. Out of the box, we have planners like actual planner, sequential planner, and stepwise planner. Still, custom planners can be created if needed, but I cannot promise this will be as easy as we build a plugin. Action Planner works by implementing an intent detection pattern, which identifies a user's intent and compares it to the functions in the registered plugins. Once it finds a plugin that most aligns with the user's goal, it uses AI to populate the necessary input parameters. All we have to do is to run the plan. The sequential planner is capable to build a plan with a sequence of steps by passing the output from one step to another. Then the plan is run in a canonical way. This is more like a waterfall. Stepwise planners is even more complex. It iterates until the goal is complete by selecting dynamically the plugin's functions and is learning from mistakes. This planner can learn from feedback while exploring available functions to figure out how to solve a problem. This is really agile, not waterfall like the sequential planner, right? So it looks like creating a planner is trivially simple. It simply does the job. The real challenge is defining good prompts, in the case of semantic functions, and choosing the right definitions, in the case of native functions. Let's summarize how can we create and run semantic functions or native functions? Well, the simplest way is to create the function alone and run it. A more elegant way is to put the function in a plugin and run it from there. In this case, we have to deal ourselves with the functions found in the plugin. How do we know which function is solving our goal? We can use a special plugin, an orchestrator. An orchestrator is able to find the best match semantically, and then it runs it. But a planner is the state of the art in finding the best functions to solve a goal, because it's using the power of AI, or the power of GPT if you like. Let me summarize again what we have so far. A planner is a pipeline consisting of one or more plugins. A plugin is a collection of functions. A function can be semantic or native. A semantic function is a prompt. In fact, text. A native function is traditional code. And the last but not the least, the kernel is the orchestrator, which loads the plugins, builds the pipeline for a specific plan, and runs the plan. But let's come back to our motor plugin. So, in the light of the latest findings, the planners, instead of using an orchestrator plugin, we better use a planner. But which planner is good for us? Action planner? Nope. It returns only one step. One function, one step. What about sequential planner? Well, let's see. It will return a list of functions, and that's a list of steps, so it looks like it's what we need. The list of steps will be executed in canonical way. We're fine. What about the stepwise planner? Well, that is good too. But for our scenario, sequential planner is good enough. Still, if we want to create a planner which gets the feedback from the environment, definitely stepwise planner is the way to go. Let me remind you, we have a car which knows some basic commands: going forward, going backward, turning left, turning right, and stopping. Before jumping to the demo, let's discuss some conventions. In order to make the sequence of steps more readable, more compact, we will convert the commands to arrows, like in the example in the last line. I think this is more intuitive too, and it's easier to follow. So let's do a demo with a motor plugin. Let me show you first this folder. This folder contains our native functions in this C# class called motor plugins. We will find here every single function annotated with sk function and with description attributes. No more, no less. Only those functions we want our planner to find. And then we will discuss later about the semantic function. We limit now to this motor plugin. And then let's go and see how we can create our logic. We instantiate a kernel. And then we create a logger, of course, because we want to have some feedback in the console. And then we import the motor plugin functions. The next step is to initialize a planner, a sequential planner. After that, we have a list of prompts, because we want to see for more prompts, not only for one. I have created a specific list of prompts. And then I will jump directly to the most interesting part. We create the plan. So we have the planner, and now we create the plan. As soon as we have the plan, let me minimize this, I don't want to spoil it. As soon as we have the plan, we run the plan. So basically, it's just a few lines of code. The rest it's, make it nice to have loggers and stuff. So let's run this. I want this to run in the minimalistic way. So my first prompt, it's go like turn left, forward, turn 9, backward. It's very, very, very simple, right? Simple, but it failed. Actually not that one failed. So go like turn left, forward, turn right, backward, and stop. This works. Left, forward, right, backward, stop. This is a convention. But then it's go 10 steps where each step is a randomly selected step, like forward, backward, and turning left or right. It says not possible to create plan for a goal with available functions. I don't know why, but definitely it didn't manage. Then another one, avoid the tree in front of the car. Well, this is how our robot is performing. It stops, turn right, and go forward. Well, good enough, but not fantastic. And one more, move forward, turn left, forward, return to the same place where it started. Well, this is not going well because it's going left, again left, left, left. Maybe it turned 4 times left. In a way, it can turn in the origin. So it looks like it's trying to do something, but let's analyze, because I have collected the results. I have collected the results for you, and I will show you in an aggregated table. So it looks like interesting. In another session, the 10 steps were generated randomly in a correct way, so maybe it was just a glitch or something. Nevertheless, it's good to compare. So it looks like I put in red those sequences which are not satisfactory. So it looks like it failed a few times. Yeah, more or less half of the times it went well, half of the times it didn't. But why is that? Let's discuss. First, a very interesting fact. GPT assumed that turn left and turn right commands are executed in 90 degrees angles. That's not bad because I didn't instructed it otherwise. And what can we do to really improve this? Did we use the semantic kernel at its best? I'm afraid not, because we created only one plugin consisting of native functions, and we expected to figure everything out from one shot. So the plugin gets some goals in a natural language, and it tries to match the function description of the motor plugins. What about if we can transform the goals into something which is more, it's closer to the function descriptions, like a list of basic commands? Not necessarily similar, it's identical word by word, but Still, we can ask for help from ChatGPT first before trying to match the native functions. So let's build such a semantic function. Well, the semantic function will prepare a list of basic commands which is much closer to the list of native functions from our motor plugin. Then, matching the list of basic commands to the native functions from our plugin will be a piece of cake. Hopefully. So, how we do that? We run extract motor command functions, which is a semantic function first, and then we will pass the output as the input for our planner. And then we run again the demo, right? Let's see what happens. Well, for me, it's just to change the flag here, and then that means our code will go directly to this import semantic function from directory, and now I can spoil it. This is our semantic function. Let's see what has specific here. Well, the settings. Temperature 0. We have some commands, some parameters. The input, which is the correction, and then the commands, which is go forward, go backward, left, right, and stop. And the prompt, let's see the prompt. The prompt says like this: you are a minimalistic car capable of performing some basic commands like, and this goes at the render time, here goes forward, backward, go left, turn left and right, and stop. And then I'm saying initial state of the car is stopped. Take this goal, and this goes the prompt, and create a list of basic commands as enumerated above to fulfill the goal. Now, the output of this semantic function will be the input of our motor plugin native functions in our planner. Let's run it. Okay, let's wait for one which is... oh, what about this avoiding the tree? I like this one. So, it says, avoid the tree in front of the car. Extracted motor commands, it's forward, turn right, forward, turn left, forward, and stop. I don't know why it stopped. But nevertheless, it looks like it's avoiding the tree and then it's resuming the direction. It's better than before. And now, let's see them side by side. Well, and overall, we have an increased satisfactory score from 53 to 80%. But how can we improve even better? As I said, it's a matter of experiencing. Better prompts, better descriptions, and maybe more semantic functions to make it clearer to GPT what we want from it. And remember one of the Schillaci laws. Ask smart to get smart. But what is Schillaci laws? Let's see below. I'm sure you realize so far that the traditional paradigms working with large language models are not very useful. We are suffering because of that. So, Sam Schillaci developed 9 principles for using large language models to create software, and Ask Smart to Get Smart is one of them. It would be interesting to try to really understand all of them. Let me summarize a few key benefits of using Semantic Kernel. Firstly, integration speed. Semantic Kernel is crafted for fast integration to enable quick application launch. Next, extensibility. Semantic Kernel allows you to connect easily with external data sources and services. Then, better prompting. Semantic Kernel introduces templated prompts with templated prompt syntax, providing you with a tool to design semantic functions. And finally, novel but familiar. With Semantic Kernel, you get the familiarity of native code alongside with the new advancements in AI, offering you the best of both worlds. All good things come to an end, and so does my discussion about Semantic Kernel. You can find a list of resources and you contact me if you need more details. Below in the last line you can find the repository for this demo talk. Personally, I hope I have convinced you that Semantic Kernel is a wonderful tool to fill the gap between your applications and GPT. So I wish you a pleasant journey in doing that. I didn't have time to get into more scenarios, but just figure out something. OpenAI is already supporting multimodal input. That means it understands images using DALL-E 2 or DALL-E 3. In the same time, Semantic Kernel supports Hugging Face service, and this works with Llama 2. Llama 2 is a large language model which works on premises, and the performance is pretty impressive. Let's say only that it's good enough. We have the pieces to assemble an intelligent drone powered by AI capable to take decisions based on some input from the camera and to take autonomous decisions without internet. Well, thank you very much for your attention, for staying here with me, and Slava Ukraini.